Okay, so now we are going to solve examples about the isentropic efficiency of the steady flow devices. First example is that we have a compressor that sucks the air in at 100 kilopascal and 15 degrees Celsius and discharges at 450 kilopascals. So if it is your compressor, it has an inlet part which has a pressure of 100 kilopascals, and then the temperature is 15 degrees Celsius, and at the discharge, the values are 450 kilopascal. Okay. Find the actual discharge temperature with isentropic efficiency of 80%. So we have the isentropic efficiency which is 0.8. This is the isentropic efficiency, assuming both cases of constant and the variable specific heat values. So firstly, I would first tell about what is the isentropic efficiency, then we can solve this example. So for this process here, firstly, let me write first we select the control volume. Control volume is the air inside the system here. So I can write the first law, which says that the in should be the same as out. And for inlet, you will have the mass flow rate, which carries some enthalpy. And since this is compressor needs some power, electric power, which will be worked out in. And that one should be equal to that the mass flow rate and the enthalpy out. These are out quantities. Okay. This is the conservation of energy. But if I write the conservation of the non-conservation, actually balance of entropy, for the balance of entropy, again, it will be steady. This one is energy. For the balance of entropy, I will write the equation now. So you will have the in will be the same as out if it is steady, and plus generation term is there. Let me erase this part. There should be generation term here. So you will have the in part will be equal to out part. Okay, but for the entropy, let me add it. Both of them are steady. This one is steady. This one is steady. But for entropy, in and out are not equal, but in plus the generation part are equal. Okay, because when you start the process with some number, for example 5, but you will end up with 8. Okay, you will have the generation additional term, which is generation. And the in properties, you remember it, we have said that there is the heat transfer and there is the mass transfer. Similarly for outlet, there is the heat transfer and there is the mass transfer. For the case here, the entropy, for the case here, this is the open system, therefore there is mass flow rate. And what will we do now? We will try to get what is isentropic efficiency. So isentropic efficiency is when I say that it is reversible, the process is reversible. Reversible means that it is frictionless. Okay, there is no any friction, and the plus, the friction is not enough. We should have the adiabatic system. If it is frictionless and if it is adiabatic, this term is 0. And the generation term is 0 if it is frictionless and adiabatic. Okay. And then this term is 0 because due to reversible part. And the adiabatic term dominates these two parts here, which is the Q dot. And you will have the M dot S in will be same as the M dot S out, and entropies will be the same. Okay. You will have the same entropy at inlet and outlet. So therefore, when the process is reversible and adiabatic, it is isentropic. And for the reversible adiabatic case, for this case, you have the maximum efficiency. Maximum work output, okay, maximum work output, or it will be the opposite of it, the minimum work input. Okay, you will have the maximum work output or the minimum work input. Okay, so the question says that the isentropic efficiency of the compressor is 80%. It means that the real Let me write it here. So the isentropic efficiency is that work input, this one will be the isentropic case, divided by the work input, and this one will be the real case. So you can see, since this one is minimum, you can see minimum work input, you should divide the isentropic case to the real one. But if it is work output, so work output, the real, you should divide this one with the work output, the isentropic. You can see the differences. If it is input, the isentropic part is on upstairs. You can see it is in upstairs, and therefore you have to get the numbers between 0 and the 1. So it will be between 1 and the 0. Okay. So you will have the numbers between 0 and the 1. Similarly here, you have to get the numbers between 0 and the 1. Since this one is minimum, it should be an upstairs. Since this one is maximum, it should be downstairs. And then for our question, which is the compressor question, it needs work input. Therefore, I will work out with this part here. So let me write it now. So that work input real, I should find it now. Work input real. For the compressor here, you can see the energy equation. It says that the mass flow rate enthalpy in plus that one should be equal to this one. So that one will be equal to m dot. So that enthalpy out minus enthalpy in. Okay. For the real one, so for inlet, I know two properties, which is 100 kilopascal and 15 degrees Celsius. Therefore, I can find it easily. So for inlet, it will be 15 degrees Celsius. And since it is ideal gas, so I should take it as ideal gas. For ideal gases, U is function of temperature only, and enthalpy is a function of temperature only. Therefore, 15 degrees is enough. And for outlet, the temperature is not given, only pressure is given. Therefore, I cannot find the outlet properties here. And now comes the isentropic case. So I will do that now. Isentropic. So you will have the mass flow rate, enthalpy outlet, which is isentropic minus enthalpy in. Okay. This will be for the isentropic case. Okay, and enthalpy inlet will be the same, H, which has 15 degrees Celsius, but isentropic enthalpy will be different. So how I will find it? I will find the isentropic enthalpy by using that S2 will be the same as S1. Okay, I will find S1 from here, from given values. Let me. So that S1 is the S inlet. So this one will be that S1 is S inlet, and at S inlet I know the temperature and I know the pressure. Okay. So therefore, I can find the S1 at inlet, and then by using the S1 at inlet, I can find the S2, the isentropic one, and working out this ratio here, I will find the enthalpy out value here. So let me write what I've got till now. So let me put it here, so that eta isentropic will be equal to. So that work input isentropic, which is that m dot, will be H out isentropic minus H inlet, divided by the work input real, which will be m dot H isentropic. H out, this one is the real one, minus the in. The ins are the same, but outlets will be different. So this one will cancel out, and you will have this final relationship here. So if you go back to the chart here, how it looks like. So you have the enthalpy versus entropy chart. So don't look at these values here. Okay. So let's say that this one is the P1, this one is P1, and this one is P2. Okay. And this is constant P1, and this one is constant P2. You can see the chart here. So you can see the compressor, it compresses from 100 kilopascal to 450 kilopascal. If I go back to here and say that this one is 100 kilopascal and this one is 450 kilopascal. And therefore, the case now, you will have two methods. In the first method, you can see this part is the entropy part, this axis, and this axis is enthalpy part. If it is real, so firstly, if it is isentropic, you will have this process. You can see entropy is constant, and you will reach to that point. Okay, entropy is constant, but this one is isentropic case, or the frictionless and adiabatic case. But if it is not real, if it is not isentropic, if it is adiabatic, if it is real, then you will have the process something like this one. You can see. This one is the real. In real one, you have the change of entropy. You can have a look at it. You can have a change of entropy. This one is the change of entropy. It goes from one process, it compresses from 100 kilopascals to 450 kilopascals, but with an increase in entropy. But for the ideal one, the entropy doesn't increase, it remains constant. That is the difference between the real one and the ideal one. But at the end, you reach the same point. Same point is you compress it from 100 to 450 kilopascal. The end points are the same, the initial points are the same, only the process path is different. Let's solve it. Okay, so let's start one by one. First, I will find the enthalpy at inlet. It is a function of temperature alone, and then for the temperature of 15 degrees Celsius, so I will go back to the tables. Okay, and I will find the value of the enthalpy at inlet for the 15 degrees Celsius. Okay, let me open the table now. Table for air. Okay, I'm going to use the table for air, which is A17. Go back to A17 here. At 15 degrees Celsius, which is 298, so sorry, 88, it's almost there. You will look for the enthalpy value. You can see it goes one by one, so that 285, 285, 290, 290, 95, 95. So you can see it goes one by one. Therefore, 288 will be the 288 kilojoules per kilogram for the enthalpy. You can see the enthalpy is the second column, and the temperature is the first column. It goes one by one. Therefore, this one also goes one by one. I can find the value of the enthalpy here. So the temperature is 288 Kelvin, and enthalpy will be 288 kilojoules per kilogram. These are approximate values. I don't have the decimal point here. You can see there is decimals here. I don't have it, but if you work out with the interpolation, you will get the decimal points as well. But this one is for the inlet. Okay, now comes to find the isentropic enthalpy at outlet. So enthalpy out isentropic. Okay, so I know that the S2 will be the same as S1 for isentropic value, and you will go to the formula here, to the first step, and we are working with the ideal gas, which is air. We are working with the variable specific heats because we are using the tables. For variable one, we are using the isentropic case. For isentropic case, we have three formulas. Which one is the best one? You can use it. Okay, which one is the easiest one? So I will use the second one again because the pressures are given. So P21 by P1 will be same as PR2 by PR1. So I'll write it here. I will use that formula to find. So P2 by P1 will be same as PR2 by PR1. Okay. This will be the formula that I'm going to use, but you should remember it is variable. CPC. Okay, and the P1 is given as 100 kilopascal. Okay, P2 is given as 450 kilopascal. If you go back to the example here, it is 450 kilopascal. And the PR1 and the PR2, so I can find the PR1, that this one is okay, because if you go back to the table here, so you can see PR values and are given with respect to temperature. Okay, if you know the temperature, you can find the PR values. It is, so therefore, I know the temperature at the beginning of the process, which is 288. So this one is the temperature, and I can find the PR value by the linear interpolation. Okay, you can use the linear interpolation, or I will use here the approximate values but it is okay that you can use the linear interpolation. Approximately it will be 1.19. Okay, as I said, it is approximate value, and by the way, so you can work with the linear interpolation and find the exact value. So I have the PR1, I have this one, and I have that one, and from here, so I will have the PR2, which will be equal to 1.19 times 450 divided by 100. Okay. And so then if you find the PR2, then you will get the values for the second point and then second state, sorry. And then from that second state, you can find the enthalpy value. So it will be 5.36. This one is for the PR2. And okay, good. Now I will go back to the table again. The PR value is 5.36. So 5.36 is here, and this is 5.77. It is 440 Kelvin and 450 Kelvin. And since it is in the first decimal point, they are the same, which is 440. In the second decimal point, it will make only one temperature difference. I will take the approximate temperature, the approximate, which is 450 Kelvin. Okay. And then if I know that the approximate temperature here, so that from that approximate temperature, I can find the enthalpy value, which is the second one. So from here, enthalpy approximately will be equal to 441.61, which makes 442 kilojoules per kilogram. Okay, so by using isentropic relations, I will summarize what I have done. So S2 is same as S1. I'm using this formula here, and the P1, P2, PR1, PR2. And the PR1, I get it from the table 9A17. So for temperature of the 288 Kelvin. Okay, this is from the table. And the PR2, I get it from this formula here, which is 5.36. Again, so from table, and we find the temperature here from the table. And from this temperature, which is 450 Kelvin, again table A17, and I find the enthalpy value. So this is for the isentropic case. I will just replace the values back here with this formula here. The eta isentropic will be equal to H out isentropic minus H1 divided by H out real minus H1. Okay, so that isentropic so isentropic efficiency is given in the question. It says that 80%, so it makes 0.8 will be equal to isentropic enthalpy at outlet, which is 442, minus H1, which is same for any of it, the isentropic or the real, it doesn't matter, it will be 288, divided by the real entropy, so the real enthalpy, which is unknown, minus 288. So therefore, real enthalpy value, so will be equal to 288 plus 442 minus 288 divided by the 0.8. So if you find the value of the enthalpy here, and then you will work out, you will go back to the table again and find the value of the temperature. And here the enthalpy becomes 481 kilojoules per kilogram. Okay, this is the real one. And the question says that find the actual discharge temperature. So it says that find temperature, not the enthalpy value. Therefore, I will go back to the table again, A17. From table A17, I will get the value of the temperature. So ideal gas properties of air, the enthalpy is 481, which is this one, and it makes, so for 480, it makes 482. And 490, it makes 492. You have the 10 temperature of 10 difference here and the 10 difference here. It goes again one by one. If it is 481, it will be 482. will be 483 kilojoules per kilogram. Again, this one is, sorry, temperature. It is Kelvin. Temperature out. Again, it is approximate. You should work out the exact units. 483 kelvins. Okay, this is the temperature that is for the real one. This one is the real. You can see in the real one, temperature at the outlet of the compressor is more than the temperature at outlet for the isentropic one. If you go back to here, if it is, let me write it here, temperature at outlet for the real one, it is 483 Kelvin, okay, 210 degrees Celsius. And the temperature outlet for the isentropic one, it is that, how much was the temperature for the isentropic? Is 440 Kelvin. So it makes 167 degrees Celsius. We can see in the isentropic case, the air is heated less because there is no friction. Okay, in this case, no friction. But in that case, a real case, you have the friction. Since there is friction, so that some of the work is used to heat some of the, the work is dissipated as the viscous dissipation, and it heats the air. Therefore, you have the much higher temperature due to friction. It's due to friction. Friction adds more temperature because due to viscous effects, you have the more temperature here. But since here there is no viscous effect, and since it is frictionless, then you have the isentropic case, and you have the less temperature. So we have another example here, which is about the engine nozzle, and it says that first let's draw it. This one is the nozzle. For this nozzle, it says that there is an entrance with 260 kilopascals and 747 degrees Celsius and 8 meters per second. These are properties at 1. These are inlet, and exit. This one is at 2, which is 85 kilopascals. And the air to gas ratio is 50, and therefore we can approximate all of them as air, which is ideal. Find the actual exit temperature and the velocity for isentropic efficiency of 92%. And if you remember from the isentropic efficiency, so first let me write the first law for this one. It will be that H1 plus V1 squared by 2 will be equal to H2 plus V2 squared by 2. This one is for real one. If it is isentropic, it will be H2 isentropic plus that V2 isentropic squared by 2. And the H2, which is this one, is real, and this one is also real. H2 real is greater than H2 isentropic. The reason, if you remember from the lecture, is the reason is that this one, that real one, has friction. Okay, therefore friction adds heat to enthalpy. Okay, that is from the lecture, and it's about the entropy lecture. Okay, if you remember from that entropy lecture, friction adds energy, heat to enthalpy. Therefore, for the real one, enthalpy at outlet is greater than enthalpy at outlet of the isentropic one. Okay. And the V2 of the real is less than V2 of the isentropic. And this is also the expected one because the friction decreases it. Okay. Friction decreases isentropic, the velocity of the real nozzle. Okay. Then the isentropic efficiency will be equal to that H2 minus H1, these are real, divided by H2 isentropic minus H1. Okay, now let's solve it. And to find the properties at 1, we will use the table A17, and the table A17, let's go to table A17. Okay, for state at 1, you have the temperature at 1, which is 1010 Kelvin. Okay, and if you go to table A17 here, for the temperature of 1020, you have the enthalpy values, which is 1068.989. Okay, so you will have that enthalpy is 68.89 kilojoules per kilogram. This is for the enthalpy 1. This is the same. And the value is given as 0.92. And we can find the enthalpy at 2 for isentropic case, and then real one we can calculate it. For isentropic one, S2 will be same as S1, and also the pressure 2 is given. Okay, and we can use the isentropic relationships. Isentropic relationship says that P2 by P1 is same as PR2 by PR1. So by using isentropic relationships, and P2 is given as 85 kilopascal, and the P1 is given as 260 kilopascal, and the PR1, it is again from the table here. It is, you can see the column for PR1, which is 123.4, and here from here you can calculate PR2 value. Okay, the PR2 value for that one will be equal to 40.33. Okay, and let's go back to chart here. For PR value, this one is the 39.27, this one is 43.35, and therefore you will use that linear interpolation. And if you use that linear interpolation, you will get the temperature value at 2 will be equal to 765 Kelvin. Okay. If you use the linear interpolation here, you will get the 765 Kelvin. And also we are requiring the enthalpy value here, which will be that H2S, because we are using the isentropic one, H2 isentropic, let me add isentropic here, because you are using the isentropic relationships here, and that one will be equal to, again by linear interpolation, it will be equal to 784 kilojoules per kilogram. Okay, so now let's go back to our formula. H1 is 1068.89, and 8.89, and this one is 784. Okay, and if you calculate the formula here, and you will get that H2 value will become, that is 806 kilojoules per kilogram. This one is the real one. Okay, and for that one, you can again go to the chart. For enthalpy value here, you can see this one is in between 780 and 800. It is here. Again, by linear interpolation, okay, we can find that T2, this one is the real one, will be equal to 786 Kelvin. Okay, this one is for the real one. And the question also says that find the velocity. Okay, for that one, I will use the formula here, which is the first law. First law says that H1 plus V1 squared by 2 will be equal to H2 real plus V2 real squared by 2. That is also the same as H2 isentropic plus V2 isentropic squared by 2. And the H1 V1 is given. H1 is that 1068, converted into the SI unit will be 1068.89 times 10 to the power of 3 joules by kilogram. And the V1 is 80 meters per second. And the H2 real value is equal to real one, it was 806 times 10 to the power of 3 joules by kilogram. And the H2 isentropic one, if you remember, it was 784 times 10 to the power of 3 joules by kilogram. Okay, you can see that I can determine V2 real by using this part of the equation. I can determine that this one by using these equations. By using these equations, I can determine the V2 isentropic. And for that one, V2 real will be equal to, let me calculate it, 728 meters per second. 728 meters per second. And the V2 isentropic will be equal to 759 meters per second. You can see it is higher because here you have the friction. Okay, this is the result. Okay.